All right, let's talk about something that is absolutely critical to electrical safety, but honestly is often misunderstood. RCD testing. Today, we're going to go way beyond just pushing that little test button. We're going to dive into what a real professional check of an RCD actually involves and why it is so fundamental to your work, to your safety, and yeah, to your legal standing. Let's get right into it.
This quote right here, it hits the nail on the head. An RCD that just sits there untested isn't safety gear. It's a false promise. It creates this dangerous sense of security that, frankly, can lead to disaster. We're here to make sure that the protection you think you have is protection you can actually prove.
So let's start with the basics. What's the whole point of an RCD? Well, it has one primary job: to save human lives from electric shock. It's your last line of defense. It works by constantly watching the current flowing in and out. The second it senses an imbalance, meaning that current is leaking somewhere it shouldn't, like through a person, it's supposed to trip. This is especially vital in certain setups. For instance, in a TT earthing system, the RCD is often the only thing that can protect you from a fault. And even in TN systems where you have other protections, the RCD is the only thing that's going to catch those tiny, low-level leakage currents that are so incredibly dangerous. And this graph shows you exactly why that's so important. We are talking about ridiculously small amounts of current here. Standards like IEC 6479-1 tell us that anything over 30 milliamps, just 30 thousandths of an amp, can be enough to stop your heart or paralyze your breathing muscles. That is the razor's edge we are dealing with. And that's exactly why the most common RCDs are rated at 30 milliamps. They're engineered to trip in just milliseconds, a tiny fraction of a second, long before that current can do irreversible damage. Okay, so this brings us to a really common habit in the industry, the push-button test. You know the one. It's fast, it's easy, and it seems like you're doing the right thing. But as we're about to see, relying on this test alone is a dangerously incomplete check. It creates an illusion of safety that could be hiding a major failure. Yeah, we all know the drill, right? Give everyone a heads up, press the test button, you see the switch snap to the off position, and you flick it back on. Job done. Or is it? See, all that button does is create a small artificial leak inside the device itself. It just proves that the physical switch, the mechanical parts, can move. That's it. It tells you absolutely nothing about whether it's sensitive enough or fast enough to actually save a life in a real fault. So let's just lay it all out. The push-button test, it only tells you if the switch can physically move from on to off, period. An injection test, on the other hand, gives you the cold, hard data. It tells you exactly how fast it tripped, in milliseconds, and at what precise current, in milliamps. It's the difference between asking, did it move, and asking, did it perform correctly and meet the legal safety standards? So let's get into the real deal. This is injection testing. It's the only way to get true, measurable proof of an RCD's performance. This is the test that the standards demand, and it's the only one that gives you a genuine health report on that device. Unlike just poking a button, injection testing uses a calibrated instrument, like this. You hook it up to the circuit, and it injects a very precise, measured fault current to safely simulate a real-world problem. And then it records exactly what happens. Now, a lot of modern testers have automatic sequences, which is great, but it's still so important to understand the manual process. And hey, a quick pro tip. Always check your tester's battery. A low battery can mess with the current it's injecting and give you totally bogus results. And of course, safe connection is everything, for you and for the validity of the test. This table really shows you what a full diagnostic looks like. We actually start by testing at half the rated trip current, and it shouldn't trip. You've got to make sure it's not too sensitive, right? You don't want nuisance tripping. Then we hit it with 1 times the rated current and 5 times the rated current to make sure it trips within the required time limits. The ramp test is fantastic. It slowly cranks up the current to find the actual trip point. Is that 30 milliamp RCD actually tripping at 22, or is it getting lazy and waiting until 29? Finally, we test at both the 0 and 180-degree phase angles to check for any weird electronic biases. This full profile, this tells you everything you need to know about that RCD's health. So why do we need all this data? Because the safety standards, we're talking AS/NZS 3000, 3760, 3012, they aren't just guidelines. They are hard, non-negotiable limits, and they're measured in milliseconds and milliamps. For a standard 30 milliamp fault, a typical standard like AS/NZS 3000 says that RCD must trip in 300 milliseconds or less. That's less than a third of a second. It's an incredibly short window, and the push-button test tells you nothing about it. Now, how often you test depends on the environment. In a commercial office, an injection test might be every year or two. But for a rental home, you're looking at testing at installation and after any modifications. The risk level really drives the frequency.
And what if the fault is bigger? Say, 5 times the rating at 150 milliamps. Well, then the RCD has to react even faster. We're talking 40 milliseconds or less. This is for those really dangerous faults where every microsecond counts. And in high-risk places like construction sites, the testing frequency goes way up. You might be doing a push-button test on a portable RCD every single day, with a full injection test every 3 months. It just makes sense. Higher risk demands more frequent proof of performance.
So, you've done the test and you've done it right. Think you're finished? Not even close. The final, and you could argue most critical step, is the paperwork. This is where your professional skill meets your legal responsibility. Those test results are your proof. And a proper record isn't just a check in a box that says pass. It needs to be detailed. You need the RCD's specific location and ID so you know exactly which device was tested. You have to state that an injection test was done, and this is the most important part. You have to record the actual numbers, the trip time in milliseconds and the trip current in milliamps. That hard data is your proof of compliance. And of course, you need the date, your name or ID for accountability, and notes on any fixes you had to make. If an RCD failed and you replaced it, you've got to write that down. Because in our industry, there's a saying, and it's absolutely true: if it's not recorded, it didn't happen. And listen, the stakes for getting this wrong are incredibly high. We're talking about massive regulatory fines for not doing injection tests. If there's an incident, your client's insurance claim could be denied because you don't have proper records. Directors and officers can be held personally liable. And in the absolute worst-case scenario, if there's a fatality, you'll be right in the middle of that investigation. Proper testing and detailed records aren't just about best practice. They are your professional and legal shield. So I want to leave you with this question. After everything we've talked about, take a serious look at your own procedures. Are you just pushing a button because it's a habit, or are you performing a real, verifiable safety test that you can stand behind with confidence? Because making that choice to use the right tools, to follow the right frequency, and to keep meticulous records, that's what makes the difference between an RCD being a true safety device or just a liability waiting to happen.